So I want to go ahead and pass it off over to Victor Lee, who is our Director of Product Management.
Thank you, Emily. This is Victor. I'm Director of Product Management, as she said. Happy to be here with you today talking about what you can do with graphs, talking to our developer and data scientist audience. With me today is Dr. Mingxi Wu, our Vice President of Engineering. He's been working in the database industry his whole career. He has a PhD, has worked for Oracle and let's see, hope I get this right, Microsoft, and he's one of the architects of our system, especially the GSQL language. So he's going to talk to us today about one of the exciting new features that we have added to the Tiger Graph platform, pattern matching in GSQL. So our agenda, which we see on the next slide, is I'm going to talk for a few minutes to give you an overview of the different types of things that you can do with graphs and show you where pattern matching fits in. Then we're going to switch to Mingxi, where he's going to go over in detail the syntax and semantics of pattern matching in GSQL. And then you're going to do some demo, because it's a feature that we've got available. It'll be shipping in just a couple weeks, but it's working. So he's going to do a live demo using some benchmark data and a recommendation application, and then we'll take your questions. So here's one way of looking at an overview of different graph cases. This is a taxonomy that Dan McCreary came up with, and he's looking not just at property graphs, but the whole spectrum of different graph databases, because he's thinking first as a user. Sometimes you're looking for performance. Sometimes you're looking for the flexibility that graphs give you, and sometimes you're looking for the unique way that they sort of naturally let you apply rules. So when you're looking for performance, that may be traversal for analytics, complex queries, deep link analytics, and so on. So this is a great view, but I'm going to take you to a different view, which tries to maybe in a short amount of time, it's easier to look at it this way. So if we go to the next slide, we've got in the center the fundamental thing that graphs give you: insight from relationships. Oops, there's something. I think there's some animation here. Can we try to click to see if? There we go. Okay, so the fundamental reason why people use graphs is because it gives you added insight by focusing not just on the entities, but on the relationships between entities. So the first way that you get that benefit is because you have flexible data modeling. You can do this sort of stick and ball modeling that people think about, and you can easily connect different data sources. So that's one thing. And if I kind of go around the circle, maybe I'm going to do the top first and then do the bottom. So rule enforcement, as we said, you can express rules about the different types of relationships that are allowed. And that kind of ties into master data management. People traditionally, a very traditional thing to do with databases is reporting and auditing. And with a lot of regulation these days in things like GDPR, there are extra requirements for how you manage your data. Institutions are also thinking about the risk they have using data to help understand their risk. Going down to the bottom, well, obviously I've got a graph. So I want to look at the direct connections. I want to look at the second and third degree of connections. I want to do deep link analysis. I want to see how many paths there are. What do I know? What can I conclude by seeing that different things are connected? What patterns do I see? And once you start thinking about those more complex patterns, then you can think about clustering, community detection, finding things that are similarly situated. What makes you similar? It's not just having similar properties, but it's having similar relationships. And finally, ranking. PageRank, which Google uses for web page ranking, is used in a lot of other applications besides just the web. So these on the bottom are the things that are sort of very graphy. And then for the analytics side. And then finally, on the right, we have the great visual aspect of graphs. People really understand things when they look at it as, you know, nodes and connections. So it's good for people to do exploratory analysis. You can have a dashboard where you're looking at graph data and you click and you make choices. Oh, I wonder what's over here. Or if you've run a complex analysis and your results are a subgraph, the results actually make sense because you can see why it showed you that. You can say, oh, I see it. I got that result because of these sets of relationships. And that comes into explainable AI, machine learning. So there's a whole sort of universe surrounding the ability of graphs to give you insight from data. So where does pattern matching come in? So it turns out, if you go to the next slide, that pattern matching is kind of like an overlay over the previous one. The pattern matching is like an overlay over the whole idea of looking at connections and the patterns that they form. So the clustering, the community detection, the paths, those are really patterns. So we're going to take a deeper look at patterns, and we're going to see how GSQL now lets you easily search for those patterns. So now we can go to the next slide. Here's just what is a pattern. I'm going to give my definition, and then I'm going to Ming-Chi will give sort of a more formal definition. But I'm saying it's just any arrangement of connected nodes which you use as a search input. So for example, if I have this little 3 nodes connected in a line like this, a person connected to another person connected to a company, say I want to find all the occurrences of this. I didn't say what types of connections they are. That's probably relevant to narrow down the results. So you probably want to specify what types of relationships. It could be person is related to person who works for this company. So what kind of data do you have determines what kind of patterns you can search for. You might have transactional data, so you search for transactional patterns. It could be social, like I said, somebody is related to somebody else. These could be events that you're recording. Transactions themselves are events, but there are other types of events. Did somebody log in to your system? Are you trying to collect security information? So you might be looking at who accesses files, who logs in, things like that. Of course, then the power comes in when you mix this type of data. Having complex graphs that merge data from multiple sources and represent different domains of knowledge, this is where you get the richness and power of what graph can do. So these hybrid patterns are really exciting. So what do you use this for? First of all, recommendation. The idea of collaborative filtering recommendation. People who bought what you just bought also bought that. That's a relational pattern. So recommendation is actually very easily explained and leveraged using graph patterns. It's also used for trying to find the bad things, the bad activity, fraud, crime. Usually these happen, there's a systematic way that crime occurs, particularly ones that require careful planning to try to evade, to subvert the system's checks against the crime. So, you know, the criminals have to be clever, so they're following a very particular pattern. And once you know how to find that pattern, then you have a weapon to work to defeat their activity. The same principle works for security, understanding risk, enforcing rules. And as I mentioned earlier, if you think from the knowledge graph perspective or predictive analytics, just seeing patterns are trends. If it's happening over time, and if it's occurring even more frequently over time, that's a trend. You can see things that you wouldn't see if you only had a limited view. If you could only look at your immediate neighbors, you wouldn't see the things that are revealed if you can take these multi-hop patterns. So you get better insight. So moving on, I'm going to give you one example, and then I'm going to switch over to Mingxi. So this is a case we've talked about before, where TigerGraph has helped China Mobile do real-time, scalable anti-fraud detection. And that was built on pattern analysis. So we had to help them train their machine learning system. What did we feed into the machine learning system? We fed into it graph patterns. So we have some graph patterns exhibited here, such as finding a little community, the many in-group connections, finding a three-step friend relationship. That's another pattern. Finding a stable group, that's another pattern. So there's real use in finding these patterns. You can, when you translate the terminology, a pattern is a feature which, and if you say feature to a data scientist, then they say, aha, that's something I use to train my machine learning. And so with that, I'll turn it over to Mingxi and let him give you a deeper insight into the new features we have in GSQL.
Okay, thanks, Victor. So I'm going to introduce the pattern match feature in GSQL that's going to available be in a couple of weeks. So what is a pattern? So pattern is a traversal trace on the graph schema. So if you think about a query writer, and when they want to ask something from the graph database, the most simple way is to declare a traversal trace on the graph and use the pattern to represent the question that he wants to match from the graph and then get the query results. And in order to facilitate people to ask us questions, and we support a regular expression to represent repetitive steps. And I'm going to give example in the formal syntax later. And a pattern in general can be linear, meaning you have a sequence of alternative of vertex type and edge type, or it can be nonlinear, meaning you can specify a tree pattern or a circle pattern that connected to each other as a subgraph. So here is a very simple example. So imagine that you have a schema that consists in only two types. One is a person vertex type, and the other is a friendship edge type. And the friendship edge type connecting to person vertex type. So I can easily specify a pattern as the first line here. Person match starting from a person and go through a friendship edge. And then I find the first hop friendship person. And then from the first hop person, I hop another friendship edge type and then reach the last person. So this is a two hop pattern. And it answers the question that given a person, how can I reach my two hop away friends? And we can write the same pattern in a succinct way in the second line. So I use a clean star here to represent the repetition of the edge type to the left of the clean star. And then to the right, I specify how many repetition I'm going to use this edge. So this will say person to the left of the parentheses can go through two hop of friendship and reach the other end of the person. So pattern matching overview. So what is pattern match? Pattern matching is the process actually finding subgraph in a data graph that conform to a given query pattern. So formally, the input will be a query pattern, P, and then a data graph, G, which is the search space. And the output would be the data graph database returns a collection of the matched instance from graph G that match to the pattern P. And it's a collection. So I use M equals to a set to represent the results. So here is a concrete example. On the left-hand side is a graph and represents a company, and the person knows person, and the person works in a company, and person involved in a product, and the company ship a product. So this is the data graph. On the left, on the right-hand side is a pattern that written by a data analyst. So this data analyst asked a simple question. Can I find a related persons who one hop away from the company the first person works for? And given this setup, the database is going to find any subgraph that match the query pattern P. So the first match is this person, person, company. And the second match, this one, person, person, company. And then third one is this person, person, company. They all conform to the pattern schema. And then the query results will return the three subgraph to the query writer. And I'm going to start from very basic syntax elaboration, and then we can go to a more complex problem solving in the end. So I start with simple one-hop pattern, and then I will show how to write a repeating simple one-hop pattern, and then I'm going to introduce the multi-hop linear pattern. So simple one-hop pattern, meaning that in the from class of GCQ, you can specify one edge type and then connecting the source and target. So on the top, I'm going to, is the classic GCQ syntax. So notice that we have the right arrow to the, so the pattern, the syntax in the before the 2.3 version, we have starting source and then dash, and then in the parentheses, you have the disjunctive edge types that you want to traverse. And then colon E1 is specify an alias for this edge types. And then you have dash right arrow to represent the direction of the data flow. And then you reach the target of the edge. And the semantics is always saying that I start from X and go through E1 or E2 or E3, and then I arrive at Y, target that binding by the alias Y. And the data flow is always from left to right. In the new 2.4 release, we are going to make it relax this to make it more declarative. So here we remove the arrow. So we just use dash dash, meaning represents the pattern match. And then in the edge type, we make a small decoration to the sides of the edge. So for E1 is to the right direction and E2 is to the left direction. And if it's undirected edge, we don't put any decoration. So this means from X, I can reach Y, where these three different edge types. So here are more variation introduction of the one-hop pattern. So most of the pattern is specified, all the pattern actually is specified in the from clause. So I omit the select and the where clause and the accum clause for the elaboration now. So for the from clause, if it's an undirected edge, I can start from X and then go through E1 and then reach Y. And E1 is undirected, so there's no decoration for E1. But we know that the X is binding to one end of the E1 and Y is binding to the other end of the E1 edge type. So you can use the alias to specify different expressions in other clauses, such as where clause and accum clause. And the second one-hop pattern is rightward edge pattern. So this E2 is a right directed edge. So it means the source of the E2 is bound to X, and the target of E2 is bound to Y. So I can always say the pattern is of E2, the source is X and the target is Y. And similarly, I bound Y to the source of E3 and X to the target of E3. And then this is a wildcard pattern. So if I use underscore without the decoration, it means this is the undirected edge binding the two ends with X and Y, and there's no direction. And the next one is a wildcard with the greater sign to represent any rightward directed edge, and the X bounded to the source and Y bounded to the target. And there are more patterns. This is the leftward one-hop pattern for leftward edge type. And then also you can use use disjunction in the edge type position. So here I combine the leftward edge type and then undirected edge type. So it means X could either be the target of any leftward edge type, or it could be one endpoint of undirected edge. And the next one is more specific one covering undirected edge and directed edge on both directions. So E1 is an undirected edge, and means X is serving as one end, Y is serving as the other endpoint. And E2 is a rightward directed edge, and X serving as the source, Y serving as the target. And E3 is a leftward directed edge, and Y is bounded to the source of E3, and X is bounded to the target of E3. And we use the vertical bar to represent their disjunctive relationship. So it means one hop, and anything that conforming to one component of the disjunction will be considered as a match. And the last one is the universal one. So we covered using underscore to represent any, and we need decoration to specify the direction. And sometimes I just want to cover both undirected edge and directed edge. Then we use the empty parentheses to represent. So this is the syntax sugar of this. So any leftward, any rightward, plus any undirected. So here's a concrete example. So this query, I start from person vertex set, and then I go through a leftward edge one hop to reach another person. So person knows person is leftward directed edge type, and then I found who knows the source. And then I can write a filter using the bounded variable S. So I say, for the seed set, I want to select whose first name is Victor and whose last name is Ahiza. And then I found the person know Victor and find their top three youngest person and return them. So this is a pattern match example. And this is another pattern match example. So this means I start from any person, I specify the person seed set at the first block. And then the second query block is a one hop pattern. I start from the seed set, and then I go through any rightward edge type, and then right to the target. But then how do I do different action based on different match types? So here in the accumulate class, we use case one. So if the target type is comments, it means I go through person related to comments edge type. Then I accumulate the comment count by one. And then if the target type is post, then I know the rightward edge type must be person post. And then I accumulate the post count to by one. And if the target type is person, then I know it's a person-person rightward relationship. Then I increment the person count. And with this single one hop pattern, I do 3 accumulation in one accumulate clause. And then I print out the 3 results. So given person Victor, I know how many comments he has made, and how many posts he has made, and how many friend he knows. So after introducing the one hop fixed length pattern, now I'm going to talk about some regular expression extension. So a lot of time when we traverse on the schema of the graph, we can do multi repetitions so that I really represent an instance by schema traversal. So for example, in this first pattern, I start from X, and then I want to go through E1 0 or more times, and then reach the target Y. But I don't know how many hops I need to reach Y. I just want to find all of them. Then I use a clean star here to the right of the undirected edge pattern, E1. So the semantic is X goes through E1 0 or more hops and reach Y. I will give example for each of this later on. So the second example is rightward directed edge E2. X is the source and Y is the target, and repeat E2 multiple times. And this is leftward directed E3 edge type, and X connected to Y, where the leftward E3 multiple times. And this is undirected edge 0 or more times, connecting X and Y. And then this is rightward any edge connecting X and Y. And this is the leftward edge connecting X and Y. And then this is a disjunction clean star, meaning that X can reach Y, where multiple repetition of either E1 or E2 or E3. And the declaration indicates their direction semantics in the schema. E1 is undirected, E2 is rightward, and E3 is leftward. And the previous slides is simply using the clean star without any bounding. And now sometime we can specify the upper bound and the lower bound of the repetition of the edge. So here in this slide, I'm going to introduce the syntax. So the first one, I start from X and go through E1. And then the clean star represents repetition. And then 2 means the lower bound. And then dot dot means I go any hop above 2. So this is lower bounds only pattern. So meaning that I repeat E1 at least twice and then reach Y. It could be more than 2. And then the second one is upper bound only. So E2 is a rightward edge type. And then clean star meaning I repeat E2. And how many times? 0 to 3 times. So I didn't specify the lower bound. On the 2 periods to the right, I specify the upper bound. So meaning that the X connect to Y, where 0, 1, 2, or up to 3 hops. And not surprisingly, now after I can specify the lower bound and upper bound, now I can really do 2 size bounds. So here, X goes through E3, leftward, and at least 3 hops, and up to 5 hops to reach Y. And also I can specify the bounds with disjunction. So X can go through either E1, E2, or E3, and then use repetition. And then I put a 3 this time without the period, the 2 dot dot, meaning that I specify an exact bound. So reach Y. So this means X can reach Y, go through either E1, E2, or E3 3 times, or the combination of them 3 times. So here is remarks regarding the repeating edge pattern. So once we use clean star in an edge pattern, we disallow the edge alias with the clean star pattern. The reason is once an edge is repeated and we don't know how many, which edge is going to be associated with a bind variable, and therefore we disallow binding alias to edge followed by a clean star. The second detail is we use we actually in GCQ pattern match, we adopt the shortest path semantic by default. So what does that mean? So when an edge is repeated with a clean star and it's a variable length, and we can find many paths for two pair of endpoints, and it's usually intractable to return all the paths between two pairs. So we consider the shortest path match only, and we found that this actually satisfy majority of the application needs we encountered in our early adopters customers. And there are other languages such as Cypher and Gremlin, and they allow, the default semantics is non-repeated edge or non-repeated vertex in the matching results. And due to these requirements, their query processing complexity is NP complete, meaning it can be very slow if you trying to find a match in a large graph. And instead, our adoption, shortest path semantics, based on the graph theory, counting an existing check of this shortest path is tractable. And tractable means there is a fast algorithm that can return the match results in polynomial time. And these are the details that we use throughout our implementation. Okay. So this is a data graph, and it consists of 6 vertices, and it connected each pair with a simple edge type E. And let's say I ask the pattern query, how do I find the matches starting from 1, go through E and reach 4? Then there, let's say I do a naive search algorithm, I can find 1, 2, 3, 4, this match. The second match is 1, 2, 3, 5, 6, 2, 3, 4. So I go through one circle and then jump out from 3 again to 4. Or any path that I go through this circle many times and jump out at 3 and reach 4. So there are infinite number of matches of this regular expression, but GCQ is going to return the first one, the shortest one. This is the shortest path matching semantics. So here is a repetition example. So I start from a tag class, and then I go through the tag class is a subclass of tag class edge type at least one time, and then reach the target. Yeah, this is one clean star example. This is another one, that exact bound. So I start from a tag class, and then I go through exactly one hop to reach the target. So after introduce the simple one-hop pattern and the simple one-hop clean star pattern, now we are ready to unveil the multi-hop pattern. So multi-hop pattern is nothing but connecting two single hop pattern with shared endpoints. So here the first 2-hop pattern, the first one is one hop pattern, and then if I look at the right side of the Y, I have a second hop pattern, and then I concatenate the source Y with the target of X. I have 2 hop. So the first hop target share with the second hop source. So this is a 2-hop pattern. With this pattern, we can extend this to multi-hop. So here is a 3-hop pattern. So I start from X, go through E2, reach Y, and then I go through E3, leftward, reach Z, and then from Z, go to E4 and reach U. This is 3-hop pattern. So you can use this pattern match in GCQ with any hop you want. And multi-hop linear pattern has some semantic restrictions at this point. Since I'm going to elaborate on this based on the implementation. So for select clause, And this pattern, let's say this is a 3-hop pattern, X to Y, first hop, Y to Z, second hop, Z to U, third hop. You can only select the endpoints of the linear pattern. So you can only select either X or the ending endpoints U in the select clause. In the from clause, you can have a succinct representation if you don't need using any of the alias. For example, I start from X and go through Y, and the edge has an alias E2. And then from Y, I go to Z, and the edge has an alias E3, and so on. And then I have E4 for the third edge. And if you don't really referring to the edge in your predicate or the accum clause expressions, you don't have to specify the edge alias and the intermediate vertex Y and Z. So here I just concatenate the edge types E2 with E3 and E4 using the dot. So X goes through E2 and goes through E3 and then E4 reach U. So I ignore the intermediate endpoints to represent this pattern. And no alias is allowed to bind to this path at this point. And in the where clause, so there's another restriction. So the where clause is a conjunction of local hop predicate only. So meaning here, so taking this 3-hop example, you can specify any predicate or condition involving X, E2, Y. This is a local hop. And then, for example, X dot age less than Y dot age. Or another local hop predicate, Y, E3, Z, for example, Y dot starting time less than E3 dot starting time, and so on. And then you can have another local hop predicate involving Z and E4 and U. And there's a special relaxation. The last hop on the linear path is Z to U. And the last hop can involve the alias of the starting endpoint X. So the last hop predicate could be X, Z, E4, and U. And clean star cannot if I have a clean star here, E2 star, then you cannot have a predicate involving X and Y because you don't know how many hops between X and Y. So clean star just represents the reachability of X to Y. Accum clause and post accum clause. Similar to the select clause, you can accum to X, the starting endpoints, and you can accumulate any summation to U, the ending endpoints. And how do we use this new pattern match syntax in the upcoming release 2.4? So we have 2 ways. The first one is using a session parameter. You set the syntax version equals to v2. v2 means pattern match syntax is extension. And if you want to stick to the old syntax, which has the single hop rightward data flow syntax, you can use v1. And if you don't specify, by default, we use v1. And the exciting feature that I'm going to demo today is the interpret mode of GSQL engine. So in the past, we have delivered the blazing fast performance for a big graph. But one obvious shortcoming is people have to wait a couple 10 seconds before the query is installed after they write the query. And this significantly reduced the interactive experience from the data scientist and the graph exploration. So we have been working on this feature for the past half year, and now we are going to release this interpret engine. And people can write ad hoc query just like SQL on the Oracle or MySQL. You can write your query and then instantly get the results. And the query is sent to the interpret engine, and the query is run while you see the results. There are 2 ways, and I'm going to demo that, so I won't elaborate here. And then the last is the query level syntax setting. So if you don't want to set universal syntax, then you can per query specify this keyword syntax after the graph name. Syntax v2 means this query is going to use the pattern match syntax. Syntax v1 means the legacy syntax. And today I'm going to demo on a relative complex schema. This is a forum, social forum schema that I borrowed from LDBC Council. LDBC Council is actually academia, interdiscipline organization spanning academia and industry graph database vendor. And they come up with this social forum schema. And so there are 45 queries testing different challenge of graph query. And the schema is actually modeling a person who are involved in different forums, social forums. So here you have person who are the main entity in the graph schema, and they can be a member of a particular forum. Forum is where the internet place you can post a particular topic. And the forum is the container of the post or other comments of the post. And then the person have some geographic locations such as city, country, and continent. And the person has some organization relationship. So person can work, study at the university or work at a company before. And also there are tag class that classify the forum and classify the message. Message is the superclass of post and comments. And the tag class is a self-connected, has a self-connected edge, is subclass of, so you can have a hierarchy of the tag. So the demo setup. So today I'm going to use the scale factor one of the benchmark query, benchmark workload. It has 3.18 million vertices, 17 million edges, and has 11 vertex type and 25 edge types. And there are attributes on the vertex types, and some edge type has attributes. I didn't list them here. And I strongly recommend people use the Docker, and we have Docker image will be published, has been published, and this is where I use the environments to run the demo. So on my laptop, I configure 4 cores for the Docker container and 15 gig for the Docker memory. And Linux swap is 1 gig, and the engine is running. So here on my screen, I'm going to show the demo. So on the left, I have one shell that connects to my Docker, and the other side is the same shell that connects to the same Docker. And I prepared the script in different files. So the first query I'm looking at is one-hop fixed length query. So in order to use the preloaded LDBC SMB's dataset, we need to use graph and graph name. And then I use this set syntax version v2 to set the syntax version, meaning that I'm going to start accepting pattern match syntax. Then I use the interpret keyword and query and empty parentheses to invoke this query to interpret engine. And the rest is the same as the previous GSQL signature. So I start from a seed block. I assign person to seed. And then I do a one-hop pattern match. So I start from all the person and find the other person who knows the seed set. So the person knows person edge is leftward here, meaning that the source of the edge is actually on the right-hand side. So I want to find people who know the person Victor. And then I sort them by birthday. and ascendingly. So the top three will be the three oldest one who knows Victor. And then I project their first name, last name, and birthday. So on the right-hand side, I can invoke this file by command line, top1 GCQ, and then it returns Aswin, Abdul, Gregorio, and their birthday. So these are the three oldest person that knows Victor. So this shows a leftward pattern match. And then let's take another look, another example. So this is also a one-hop query, and I test rightward edge type using the wildcard underscore. Still, I start from person, but this time I use wildcard to indicate from Victor, I can go through any rightward edge type and reach target. Then how do I differentiate different edge type? In the Qm class, I use case one to check different condition. And based on different condition, I do different accumulation to Victor. So here, if the target type is comment, then I increment the comments accumulator, which I declared here as a sum accum. If the target type is post, I increment the post account, post account accumulator. If the target type is person, I accumulate the person count accumulator. And after this pattern match, I projected the comment count, post count, and the person count of the result set. So let's invoke this with the interpret engine here. So this one will do accumulation. So it returns the results instantly. So Victor has 25%. Victor knows 25%, and he has made 152 comments and 96 posts. Okay. Then let's take another look of third example, one-hop disjunctive edge pattern. So this time, we go through two different edge type in one hop, and I use the vertical bar to indicate their disjunctive relationship. So we want to find people who knows Victor or the person that Victor knows. So this two different direction of the edge type. Either someone knows Victor, which is from right to left, or Victor knows someone which is left to right. And we use the where clause to select Victor because seed is all the person. And then we order by the relevant person to Victor by the alias p.birthday ascendingly. And then we limit the result set to be 2, meaning that we are only interested in the two oldest person that relate to Victor. So we can run this Python query now on the shell command. So the two person that relevant to Victor is Abdul and Gregor. Okay. So now let's take a look of the star pattern. So I'm going to open the first star pattern example here. So I used a tag, semantic tag as a traversal example. So I start making tag class to the vertex set tag class 1. And then once I assign tag class to tag class 1, I start traversal. So tag class 1 do one star hop traversal, and the tag class is a subclass of a tag class. This edge type is rightward. And I put a clean star here, meaning I want to find tennis players. Here, the where clause I use filter, tennis player tag. I want to find the super class of tennis player, regardless how many hop away it is from the tennis player. So I don't specify any bounds. So this is any reachability query. So I can do this on the command line on this *1 file. Okay, it returns all the ancestors of tennis player. So here, agent is one ancestor class, tennis player itself is one ancestor, and then thing, athlete, and person. So this is without any bounds. Then let's take another star example. So this example, let me so also I want to start from tag class and select the tennis player, and I want to find the one hop away superclass. So here I use *1 indicate there's only one hop, exactly one hop to reach the superclass. So I can run this query using the interpret mode, and then I found actually athlete is the immediate superclass of tennis player. Okay. Now let's take a look of the third star example here. I still start from tennis player, and then I use the same tag class is subclass of tag class edge type. This time I specify the lower bound and upper bounds at the same time. So it means I want to find the superclass of tennis player, which are either one hop or two hop away from the tennis player. So this one I can run here. So we found athlete and person. Let's take a look of the fourth example. This one is the upper bound example. So I want to find within two hop parent class of tennis player. So invoke this with command line, sending this query to interpret mode. And then within two hop, we find athlete, person, tennis player itself as the superclass. Okay. Now let's take a look at the last star example. So this one is, I want to start from person. So here, seed, I assign person to the seed. And then I start from person set. And then I want to find all the comments that's created by the person, which is connected by the comment has creator person edge. So this comment is created by one of the sets here. And then all the comments that the person likes. So basically we are answering the question, find the top 3 latest comments that is either liked or created by Victor. And then we also want to return the total number of comments related to Victor. So the where condition specify the filter of the seed. I want Victor being the seed. And then I accumulate the relevant comments by a global accumulator comment count. Any match to this pattern will increment the accumulator comment count. And then I order by the comments. The comments is either created by Victor or it's likes by Victor. And then I do a descending order of the creation dates of the relevant comments, and then I return the top 3. So I return the latest 3 comments that are relevant to Victor, and I also return the total number of comments relevant to Victor. So this is a star query that with disjunction. So we can see that this comments created on 2012 September 4th is one of the latest related comments to Victor. And this is another one. And the total comments related to Victor is 152 in the graph database. Okay, after seeing the one-hop fixed length pattern and one-hop star pattern, now we are ready to present the multi-hop pattern. So here, let's take a look of multi-hop pattern here. Oh, this is a really long pattern. I'm trying to adjust the screen. So I still start from the tag class, and then I go through the tag class, this subclass of a tag class, and then I use the succinct representation. I don't need to refer to any intermediate vertex, so I use the dot to connect to the next hash type. So the next hash type is the same as the first hash type, and then I do the same for the next hash type. So straight hop, I find my parent tag class, and basically this question, this query is asking what are the third ancestor of tennis player in the tag class class chain. So we can run this multi-hop example, and it returns agent. So agent would be the third superclass from tennis player. This is another example, and it's a two hop. Well, the first hop is a disjunction. So I start from message. Message is either comments or post. And I want to find each message original country. So post is located in country or comment is located in a country. And then from the country, I want to find which continent this country belongs to. Then I use country as part of continent edge to connect to the target continent. So this is the disjunction followed by one hop to the continent. And it's a single directed edge in the pattern. And then the filter says, I want to find the message whose creation date is 2011 and month is January. And these two predicates of this purpose. And then I accumulate the continent name into the message. And then I order the message creation date and limit 3. Then finally, I return the top 3 latest message, which are created in January 2011 and their continent. So this is the multi-hop. So I found the top 3 message. Creation date is always 2011 January, and the continent name we put in accumulator called continent name. So one of the top 3 messages is created from Asia. The second one is Europe. The third one is also Asia. Okay, this is a multi-hop example of pattern match. So after seeing the basics, now we are ready to present application. So I'm going to focus on the recommendation engine. So the first recommendation is based on similarity. So I use syntax version 2, and then I set the query timeout to 1 minute. So each unit is 1 millisecond. And the query will, this time I don't use the interpret keywords to start the query. Instead, I use the traditional create a query name. And then if you look at the query body, after the query body, I actually call interpret query name. So I can do the query creation as the pre 2.4, and then this query will be added into catalog. And once it's in the catalog, instead of using install query recommend message, this time I call interpret query and the query name with the query parameter. Then you basically invoke this query immediately. And if you are satisfied with the query results, you can still do the traditional install query and then run query, two-step invocation. But it will take 1 minute or 10 seconds to compile the query, to optimize the query. So now I'm going to explain the recommendation algorithm. So these are the accumulator I'm going to use in the query body. And here I start with all the person, and the seed include all the person. I use a where clause to filter the person who has the first name and last name input by the query parameter. And then the first thing I want to do is find all the message that the input person likes. Likes. So the message could be a comment or it could be a post. And then I leave a set effect on those messages that has been liked by the input person. The set effects, I use a Boolean expression, Boolean accumulator or accumulator liked, and then I set it to true. Basically, I start from the person, and then I find all the message that has liked by him or her, and then I mark them as liked. Then the next thing I want to do is find other people who like the same message that the input person likes. Then I start from the seed and still use the where clause to find the input user. And then I go one hop, find the message. So the one hop could be a person likes comments or person likes a post. And then since I don't need the intermediate message alias, so I use a dot, and then I connect to the next one. So I will do comments or post as tag. So I found those message tag or semantic tag, and then reach the tag vertex type. So basically, I'm doing the thing that the input person likes some message and post, and those message and posts belongs to a tag. And then from the tag, I find other message that belongs to the tag using the comment hashtag, post hashtag, and then I do another person likes comments to using the leftward edge type, and then person likes post, and then I find the other person. And then I count how many tag in common with the input person. I use the tag in common accumulator and accumulate this in common cardinality into the target person. And after this accumulation clause, I can compute the similarity score. So here, our similarity score of person P to the input person S is basically based on how many tags in common between their liked messages. And then here I bring the similarity into the log space, and 1 plus this common tag count, basically avoid the 0 score. And then every person now has a similarity score relevant to the input user. Once I calculate the similarity score for each person, now I'm going to do the recommendation. So the recommendation is basically from the person to voting of the message that has not seen by the input user. And we filter the input user by message likely equal to false, meaning that the input user has not seen it. And then I do a cum rank. And the rank is basically a summation of all the other people who has voted the like of this message. And each other person already has a similarity score representing their similarity to the input user. And then after sum all the similarity score of other users, we get a rank for each message. Then we order by the message rank and then return the top three biggest similar message. And then we recommend this message to the input user. So I can run this recommendation algorithm. So it's going to touch all the messages and starting from the input user. So it's going to take some time. So the top three relevant message to the input user is this one, who has rank 4,828, and this message, and this is the ranking score, and this message, ranking score. Okay. So now I'm going to talk about the second recommendation algorithm. So this time I use the cosine similarity to find the similarity between two persons. And as a review, cosine similarity given person A and person B, in order to find their similarity, we need to find their commonality first on the nominator. And A dot product B means their common likes. And then the denominator is the square root of A's likes, and then times the square root of B's likes. And then this will give you the cosine similarity. So the high level flow is for each other person, I want to find the similarity score, cosine similarity score relative to the input user A. And then once each other person has a similarity score of A, we can use that similarity score to vote the message that A has now seen. And then we return the highest voting message as a recommendation to input user A. So here, as usual, we declare some accumulator we are going to use during the traverse of the graph. And then I start from all the person. The first step, I want to mark all the message that has been liked by the input user. So the where clause is selecting S as the input user. Fn is the input parameter. Ln is the input parameter. And then for each message that has connection to the person, input person, where the lex comments or lex post edge, we mark the lex equals to true. And then for each, also we record the total message count for the input user. So this can be done in one accum class. And we put the total input person message count into a global accumulator. And we just take a square root. Remember the similarity score is the square root of A square, and this is to stay the same throughout different person B. So we just store this constant in a global variable. And then we are ready to find the similarity score for the other person. So I start from the input person. Since the first hop, I already decided the input person. And then this time I use the common likes message to connect the input person and other person. So first I go from the left to right, go to this disjunctive pattern to reach the message that the input person likes. And then from the message that the input person likes, I go a reverse direction to reach the other person who also likes this message. And for each other person, I accumulate the message in common accumulator by 1. At this point, I already got the common message between A and B, which is the dot product A and B. I store them in the message in common local accumulator on each person. So the next thing is I need to find the B square, which is the liked message from person B, independent of person A. So I go to here. I start from the other person that's relevant to the input user, and then I find the message that has been liked by the person, and where this disjunctive edge pattern, and then I accumulate the like. I want to make sure this message are not liked by the input user, and oh, sorry. Actually, this is the next block. The next block, after we talk about this block, we want to record the similarity of other person. So at this point, we need to know the sum of bi square, which is how many liked comments or posts the other person have. And then we use this edge pattern and then accumulate here. This will be the bi square sum. And then in the post-accum clause, I can compute the cosine similarity. Since I already have this sum ai square in the global accumulator, I have the dot product in the message in common, and I have the square root of bi square sum in this message count. Then I plug in this formula, O dot message in common, which is the dot product, divided by the square root of input person message count times the square root of the individual message count. And then I posted the similarity score onto the person. After this block, every person has a similarity score to the input person A. Now I'm ready to do the recommendation. So for each person, I go to the other message, and this message should have not been liked by the input user A. And then I accumulate the rank. So each person can carry a similarity score, and then their score is summed in the rank accumulator. And then finally, order by the message rank descendingly, and then return the top 10 as the recommended new message to Victor. So here I can switch to this screen, invoke this similarity score recommendation engine. And you can see that I just start using the graph and then do the recommendation into the interpreting engine. So it recommends 10 message. The first is this one, second one has this rank score, and also shows the recommended message. Yeah, I think this concludes my demo. We will upload all these scripts, including the schema setup and loading data script into GitHub, so that user can reproduce using our developer edition.
You can download the developer edition from our website at tigergraph.com/developer. You can run it in Docker, or you can install it on your own computer, on a Linux computer. And lastly, you can get other information from our website. We have Graph Guru's web hour. It's online office hours every Thursday. So tomorrow at 11 a.m. Pacific, if you have any questions, you can send them in advance or just drop in. If you missed this, want to see this webinar again, or we have lots of information at our website, a developer portal. We have the files for the demonstration for this Graph Gurus, as well as all the previous ones. And we have more questions and answers on our developer forum, and where people are discussing issues. We're on social media, of course, and so we just want to thank you again, and we hope to see you next time.